All right, so now let's take a look at what's going to happen in this particular lesson here today. So you may recall one of the things that we did way back when is we proved that the diagonals of a rectangle were congruent. Now, traditionally, the idea is to draw a rectangle and use overlapping congruent triangles. You can use something along the lines of side angle side here. And as an exercise for yourself, it may be a good idea for you to actually just very briefly sketch out a proof of this yourself to make sure you understand how it's done. Now, note that now we have the technology, I suppose, of analytic geometry, which means that we can actually start thinking about this completely analytically. So, for instance here, what we can do is we can sketch what's going on. As always, you always want to have a nice sketch here. So here's our sketch. Now, remember, note that this is going to be true for any rectangle here, any rectangle at all, which means that we actually don't know anything about the coordinates of the rectangle here. So, in particular, if we have a rectangle like this, a rectangle, for all intents and purposes, could look something like this here. I'll call this P, Q, R, S, right? This could be our rectangle like this in the coordinate plane here. And because we don't know where any of the coordinates are, we're going to have to use variables. So we're going to say, for instance, this AB, this CD here, this EF, this GH. And note that here in this situation, all we have to do to show the diagonals are congruent is just to show that PR and QS are the same by using distance formula. Unfortunately, however, that's 8 variables, and 8 variables is a lot. So I'm wondering if there's a way we can sort of reduce the number of variables that we can deal with here. Now, one of the weird things about this problem is that this rectangle is in some random orientation here, right? Wouldn't it be nice if the rectangle, were behaved a little bit better in a way? So one thing we can consider is we would love for this rectangle to sort of be, straight. We can straighten the rectangle by rotating it so that it's parallel to the axes here. Now, some of you may wonder, wait a minute, what allows you to do that, right? How do we know that that's not going to change it? Okay. That's a perfectly valid idea here. What guarantees us what allows us to do something like this here, right? So what we would like to see is the rectangle sort of rotated back so that the sides are parallel to the axes here. Now, if you're not particularly comfortable about that, if you don't like moving the rectangle because you think the rectangle could be in any general position, if you don't want to move the rectangle, move the axes. What if we redrew the axis so that it looks like this? And then we can force, I'll call this the X hat axis and the Y hat axis here. We can create new axes like this so that these red axes are parallel to the sides of the rectangle here. So even, basically it's just a matter of perspective here. Even though technically we can, it doesn't seem like we should be able to move the rectangle here, we can actually move the axes so that we can create that picture here. So we're going to go ahead now, therefore, and create this picture here. So now the picture changes so that now we've reoriented the axes, so it looks like this here. And our rectangle now looks like this. That behaves a lot better. Now, why is this better? Well, let's have a look at this. Maybe we can determine what's going on here. P is still going to be at some point AB here. We still don't know where it is. Again, these are all dummy variables. But the nice part about what's going on here is that now this is horizontal, right? So the horizontal thing means that the Y coordinate remains A, so that D actually now becomes B, right? We can still call this C because we don't know where it is. And then R, as you can see here now, and then by the same token, we can do this with S, right? So in this case here, again, because it's a vertical line here, just like in the example that we looked at the beginning, the X coordinates are going to remain the same. So there's going to be A, comma, H, right? And we don't know how far that is. And in R, we can see that R is actually now completely determined. It's going to inherit the X coordinate at point Q and the Y coordinate at point S. So now it becomes this. So notice what happened here. Over here, we had 8 variables. But here, we only got A, B, let's see, we have A, B, C, and H. There are only 4 variables now. So note that the nice part about this is that when we rearrange the rectangle so it looked like this here, we actually reduced the number of variables. So instead of dealing with 8 variables, we know how to deal with 4, and that's actually quite nice. Now, some of you may ask, can we do better? Can we reduce the number of variables further? Now, note that in this situation here, again, we had either control the rectangle or control the axes. So one thing we could do is maybe we can move it around. Some of you may know, wait a minute, what would happen if I were to zero out some of the variables? What would happen if I were to shove point P to the origin? If I were to do this here. Now some of you may note, so let's go ahead and sketch that out. Some of you may note here that if we were to do that, okay, we were to shove to the origin here. Now our picture looks like this. Note that AB is now 0, 0. That makes A and B 0. So that means S is going to be at the point 0, H. I mean, R is still going to be at some point CH here. But Q is going to be, now again, B is 0, so it's going to call it C, 0. Note that the variables here, again, these variables are just dummy variables. They're placeholders. They don't necessarily mean the same thing. This C and H here is not the same value as this C and H here. The point here is that we've actually eliminated a lot more variables, and now we're down to 2 variables in this case. So you may ask, wait a minute, can't we do even better? Can I go even further? Can I make it such that H is equal to C? So we have only 1 variable. And that is a valid thing that you may want to think about. But note that in doing so, you may have gotten yourself carried away. Because if we call this C, C, that implies PQRS is a square. And note that the claims that the diagonals of a rectangle are congruent. While a square is indeed a rectangle, not all rectangles are squares. So you have to be kind of careful when you're doing this sort of thing here. You have to be kind of careful that you don't accidentally oversimplify and make it such that it doesn't apply to the entire situation that you're dealing with. We want to deal with the general rectangle here. By making C equals H, we would create this only for squares, and that would not be valid. Okay, now that we've set it up here, now we can go ahead and actually do this thing here. So we want to find the diagonals of a rectangle congruent, so we're going to go ahead and write this out here. And in this case, I have to show that PR equals QS, right? So now we can go ahead and calculate this. So let's see here. So let's look at our picture. So PR here is going to be the square root of, all right, so PR, that's actually quite nice. It's going to be C minus 0 squared plus H minus 0 squared. And that's going to be the square root of C squared plus H squared. And that's what we want to see here. And now we want to do the same thing for QS. And again, distance formula is going to help us here. It's going to be 0 minus C squared plus H minus 0 squared. And that is negative C all squared plus H squared. And that is indeed the square root of C squared plus H squared. And we see that we have a match. So note that now we can say that thus, since PR equals QS, the diagonals of any rectangle must be congruent. And we finish, okay? So note that, again, just like with the standard coordinate geometry proofs, you want to be able to write this out. You want to have a nice little statement here at the end. So, the best way to think about this here, notice that we can do this with any sort of, we can actually do a lot of things with this here. Now that we have the technology of analytic geometry here, we can actually do a lot of things that we did in standard, synthetic geometry using using side angle sines and things like that. Now we can do that here. So the idea behind this, and you can see when you're trying to set up a proof for a general theorem here, you want to try to make many coordinates 0, because that zeros are relatively friendly numbers and they keep things nice. So you often accomplish this by, as you can see, by placing as many vertices on the axis and sides along the axis as possible. Note that in your original setup here, you can place the figure wherever you like, right? And you can even put your sides wherever you like as well, just as long as you make sure that your general figure actually does satisfy what's looking for here. Okay.